Sally Price, Fellow of Royal Society, Fellow of Royal Society of Chemistry, is a theoretical chemist who did a bachelor and then PhD at Cambridge University under the supervision of Professor Anthony Stone, working on modeling the intermolecular forces between two hydrogen molecules. And this seminar is actually operated from the department where Professor Kowos was studying hydrogen molecule long time ago, and he's the founder of theoretical chemistry at our department. She then went to University of Chicago as a postdoc, working with Jeremy Bardet, before returning to Cambridge to continue work with Anthony Stone on developing anisotropic atom-atom intermolecular potentials from the charge densities of the molecules. On getting a lectureship at University College London, her first grant was to adopt a crystal structure modeling code to use distributed multiples for rigid organic molecules, starting the development of the ACRIS, which now uses a range of anisotropic atom-atom intermolecular potentials and is used in organic crystal structure prediction and property modeling. In 2004, she led a large consortium project, Control and Prediction of Organic Solid State, CPOS, which developed organic crystal structure and property prediction simulations in collaboration with a wide range of experimental and computational scientists. She's currently a leader of the in silico working group of the cost action best CSP. Sally has been author of over 200 scientific papers. She was elected Fellow of Royal Society in 2017, and today Sally will present her lecture, Organic Crystal Structure Prediction, What is Needed for Confident Prediction of Polymorphs. Sally, the screen is yours.
Thank you. And this question is one that is very important to the pharmaceutical companies because of examples that they've had like this. So this is a transdermal patch used for treating Parkinson's disease. And I hope you can see that there are crystals that have grown in it. And these are of a more stable polymorph and therefore a less soluble polymorph than they knew about when they designed the patch. So this sort of bombshell that really disrupts and causes a lot of problems for the pharmaceutical company. It was shown in 2019 that this could have been avoided, in this case, using the codes of one of the commercial companies that do crystal structure prediction, that they could have predicted that this crystal was there and could have been formed and could have avoided this disruption. But this sort of problem is just one of the examples why we got funding for developing crystal structure prediction in conjunction with experimental work. And today I just want to give you a flavor of what is behind why this is such a difficult question to answer. And I'm going to be calling on a lot of work, and all the references in blue are on the CPOS website. Please just look at the names which are acknowledging the contributions of a lot of the authors. So polymorphism is a problem and has been for a long time. As Walter McCrone famously said, it looked as if you got more polymorphs the more you worked on the system. More recently, it was shown by comparing the screening data of looking for polymorphs from two companies that the vast majority of the active pharmaceutical molecules were polymorphic. And part of the reason for our increased knowledge of polymorphism is what most of you will be aware of, how rapidly the methods of detecting and characterizing crystal structures have been evolving recently. Not only the sort of structures that you can handle by single crystal X-ray diffraction, but also powder diffraction, increasingly now electron diffraction, and also solving structures solid state NMR. Though some of these methods are helped or can use the information from a crystal structure prediction calculation. The other thing that's been evolving is the range of experiments that can produce the first sample of a new polymorph. These are getting more and more diverse. There are now robotic automation for doing the obvious masses of screening of solvents and rate of cooling, etc., for solution crystallization. I'll be looking a bit more about cases of heterogeneous nucleation, but there's also a lot of work on melt crystallization, crystallization under pressure, crystallization under confinement. You might be wondering why any interest in methods that can't be reproduced, but this is because given your first sample of new crystal structure, you may then be able to use it to seed and produce more samples, particularly if it is a more stable form. The other aspect of why polymorphism in organics is a problem is that it does contrast with inorganic structures where you can get hundreds of different systems adopting spinel or perovskite structures. The nearest equivalent you have in organics is perhaps taking a scaffold and then adding small substituents to it. And we did an analysis of 232 structures, which were just this scaffold with simple substitution, one on each ring maximum, and nothing larger than the phenyl, a lot of them halogens. And make a mental guess now of how many different structures were adopted by those. We were lucky to have so many because this is a core for drugs, agrochemicals, fluorescent probes, and also there was a collaboration between a University Gonzaga where they had a lot of undergraduates synthesizing simple chalcones, and colleagues in Bristol helped them with solving the crystal structures. But notice to have got the crystal structure, the molecule must have been synthesized and crystallized relatively easily so that it could be solved by single crystal diffraction. Hopefully you've got your estimates. Clues: the space distribution is perfectly normal, many monoclinic or triclinic space groups. Not much polymorph screening, so there are not that many polymorphs known, and the number of molecules are down, but a lot of the structures had more than one independent molecule, so we have more unique conformations. So we did an analysis, and to our surprise, 232 crystal structures generated 170 different packings, either on the basis of being able to overlay a 20 molecule cluster, ignoring molecular differences, or from the XPack analysis, which is more dealing with the long range order form. And this was because the largest, by far, set of isostructural crystals only contained 15, mainly parasubstituted halogens and methyls. This was not so incompatible with having a favorable packing of the dominant part of the molecule, which is the core, because a CSP on that core showed that there were multiple ways of packing it that were favorable. So crystal structure prediction, and I'm going to call it CSP because you'll be seeing it isn't what most people might have expected a crystal structure prediction code to do, of just predict the crystal structures you know about. This evolved initially for curiosity to test theories for predicting crystal structures, but rapidly became recruited as an idea that it should be able to aid the design of new functional materials. We got our first funding for developing the modelling from an organic nonlinear optical initiative, because they'd synthesized so many molecules with high nonlinear optical properties that then crystallized in an centrosymmetric and then inactive crystal structure. And it's also increasingly used now just to aid the polymorph screening and the development of specialty organic products, particularly pharmaceuticals. And this comes from this very important link that the crystal structure prediction gives you the specific polymorphic structure, and it's that specific structure determines the properties, whether they're the functional properties or the spectra that you need for identifying the polymorph in any monitoring and looking for polymorphs, and also the properties that are important in processing it, such as the solubility, morphology, growth rates, and all of these interact to give you your performance of your product, including its stability, and for drugs, the dissolution rate is a key aspect. So this idea of how you go from the structure and this interrelationship led to the digital design vision that was behind a project organized by Eli Lilly. Their authors are in red. And the idea was to see whether we could go from the chemical diagram using no experimental information on the molecule itself through to knowing how you would manufacture that as a crystalline product. Conceptually, you'd use crystal structure prediction to find the possible forms, refine the thermodynamics to get your landscape and phase diagram of the possible structures, use these to calculate the morphologies and the growth rates in different solvents, the solubility in different solvents, and also in biorelevant media, and select which structure you wanted to manufacture. And you can put all these parameters into a chemical engineering n-dimensional population balance model to predict the resulting particle size distribution and particle shape distribution, and therefore choose your manufacturing product, solvents, process conditions for that molecule, or decide that it's going to be too hard to process. Spoiler alert, we tried this on succinic acid and olanzapine and could show that there are still major challenges for this conceptually fine idea from the degree of polymorphism and the competing crystal forms, and our inability to model the nucleation rates you need. There are also quite a lot of limitations on the accuracy with current computational model, because so many of the features are exponential in the energy differences. So, crystal structure prediction, there have been Faraday discussions on it, lots of work on it, but it's based on the simple assumption that a molecule will crystallize in the most thermodynamically stable structure. And on that assumption, all you need to do is to search through all possible crystal structures and find the most stable. So the search is actually quite a major challenge because of the size of the search space, which, even if you've only got one independent molecule in the unit cell, we may be considering millions of structures before we feel the search is complete. And the search size increases drastically with the number of independent molecules where you've also got their relative positions, and the degree of molecular flexibility and shapes that the molecules can adopt within the crystal structure. We approximate in the first instance, so a 0th order model, the stability by just looking at the lattice energy, which is the energy to separate an infinite perfect static lattice of the crystal into infinitely separated molecules in their lowest energy conformation. And this becomes very energetically demanding. But there are lots of approaches on all sorts of things, aspects of this, that have been periodically tested by the Cambridge Crystallographic Data Centre in blind tests of can we predict crystal structures. This is the result of the latest blind test. The papers are now out, and I haven't listed the more than 100 authors covering the 24 groups who participated in this test. You can see the variety and standard of molecules that were being covered. And there were a few groups that were consistently successful, including 2 of the companies that do crystal structure prediction for the pharmaceutical companies. But the successful method did come at a huge cost in terms of CPU and the computer time, as well as the manpower involved. And if you ask me who was the winner, I think it was the molecules, because they had actually done and commissioned experimental polymorphic screening on all the systems in the blind test. And virtually all of them came out with a polymorph that was sort of outside the model that we use for crystal structure prediction, with quite a lot of problems of disorder and also some disappearing polymorphs that couldn't be reproduced. So things are advancing, but the experiments and the molecules are also moving forward very rapidly. So to give you an example of this, CSP usually will find the structures of the known polymorphs as low-lying minima that are generated by a CSP study. But the big problem is that it over-predicts the polymorphs. So here's a 2014 CSP on this famous system called ROY, because it's red, orange, and yellow. And you can see that you can physically see that the polymorphs differ. And this is the first diagram here, where every point is a local minimum in the lattice energy of this molecule. The ones corresponding to the experimental structures that were known at the time are the points that are red diamonds. But you can see there are an awful lot of other structures, far more than the number of structures of the polymorphs that had been observed that didn't have the crystal structures available. Now, since that 2014, a couple of those structures have been solved, Z prime equal 2. Another one was found, pumpkin orange, in 2013, where from the powder pattern, perhaps you can see the crystals, you've got some yellow ones mixed in with the new form there. Solving it from powder pattern was helped by using the CSP results. But nonetheless, when far superior and more accurate computational methods were used for the energy in 2022 to revise this landscape, they nevertheless came out with the conclusion how many more polymorphs of ROY remain undiscovered. And I think they're up to 13 now. They keep on being found, but there are so many more being generated by the calculations than are known. Now, this might sound like this is academics working on this system. What about an industry? Well, we were lucky to work with Eli Lilly on this drug molecule for the CSP, where we ended up with 10 polymorphs with characterized crystal structures. And this was a heroic effort at screening. And you can see for the CSP that there are lots of spots on there, masses of crystal structures that do not correspond to known ones, including this global minimum, which was therefore a danger sign that there was a more stable structure yet to be found. Now, this system was hard to work on experimentally because it readily formed the monohydrate. In fact, it would crystallize with many, many solvents. So to get solvate structures rather than neat polymorphs, but also it decomposed on heating. So actually only 2 of the polymorphs could be grown by single crystal diffraction, classical growth, and solving the structure. The majority were desolvated solvates, and we were using the CSP generated structures to help solve these structures from the powder patterns. And when Form 8 had multiple solutions, we then went through calculating as well as measuring the solid state NMR of all of them to confirm these structures. There is still the denser global minimum. So they commissioned Colin Pullum in Edinburgh to try crystallizing this under pressure. And that did find one more polymorph, mainly because the pressure enabled Form 5 to be melted and then recrystallized. It still hadn't found the global minimum. After we published it, Greg Barron used a really good calculation on the monomer correction and showed that actually the known Form 5 was more stable in lattice energy than our global minimum. So there are real major challenges in crystal structure prediction for the theoretical community. There are 2 different approaches widely used. One is the approach of doing your quantum mechanics on all the low energy crystal structures that are competitive. And I think many in the audience will be familiar with methods of using periodic electronic structure calculations, such as plane wave density functional theory. But you've got to have a dispersion correction added to this, because to be affordable, we are right the way down at the bottom of the Jacob's ladder of functionals. Usually for optimizations, people are using functionals like the PBE. There's been development in the different dispersion corrections. These calculations are very CPU intensive, but there is a lot of work being done on developing these methods. But as electronic structure methods, there's no hope of them being used in molecular dynamics. Our approach that started 3 decades ago is just to do the wave function calculation on the molecule. So you use the quantum mechanics of the molecule in each conformation to get the intramolecular energy penalty of deformation of the molecule from its lowest energy conformation, and also the atomic multipoles that model that charge density at that conformation, which we can use to calculate the electrostatic contribution to the dominant intermolecular energy of the crystal. So we've got non-spherical atoms having distributed multipole analysis for the electrostatic energy. And this proves crucial for modeling the orientation dependence of the hydrogen bonding and pi-pi electron stacking, etc. The other terms in the examples I'll be given have mainly been empirically fitted to crystal structures in the XX model, but there are a lot of non-empirical methods of getting the intermolecular potential modelled as well. And this approach of anisotropic atom-atom potentials have better prospects for being useful in molecular dynamics if we could add an analytical term for the intramolecular conformation. But it's worth noting that in the blind test, many of the most accurate methods were a mixture of hybrids of these approaches. For example, doing extra calculations on the monomer to correct the electronic structure determinations on the crystal. And it's also perhaps worth emphasizing here that from the early blind tests, it was clear that the traditional molecular dynamics force fields were not reliable, often pretty hopeless for crystal structure prediction. And the differences between the approaches are important. Eli Lilly were in the good position where they could compare for Roy the published search I saw earlier with one done by the company's guard simulations software, and just look at the overlap of the lowest 100 one molecule in the asymmetric unit crystal structures. Okay, the overlap contains many of the polymorphs, doesn't contain one of them, and neither of them contain one of the known polymorphs. In our case, it was 2 above the top 100, and it isn't even a minimum with the periodic PBE dispersion correction calculations from the dislocalization error. To be fair, the drug molecule I showed you at, the calculations based on just doing calculations on the molecule gave an even larger preference to the hypothetical global minimum that has not been found. And both methods led to costly pressure work, which could have been avoided if we'd had more accurate calculations. So I hope you've seen from here that crystal structure prediction calculations, it's dependent on relative energies, and there's a lot of cancellations behind its success. This will depend on the molecule, because it depends on the molecule what aspects of conformational energy changes you are balancing with which intermolecular interactions, such as hydrogen bonding, halogen bonding. But you've always got the van der Waals dispersion, which of course is a real challenge to the theoretical community to evaluate correctly. But it also depends on the differences in the range of crystal structures. Here's strychnine, where there is such a large energy difference of about 10 kilojoules per mole between the lowest, and it is the only observed crystal structure, and the rest, that you can be pretty confident it won't be polymorphic, and it doesn't really matter how accurately you calculate that large difference. But this we now understand to be rather rare because it requires the packing of your molecule to be uniquely favorable, defining all 3 dimensions of your crystal structure. But let's go beyond this. This was just talking about this lattice energy, the static idealized model, which needs an affordable methods for many structures, and we're still working on that. But we know that many systems switch their relative stability with temperature. And of course, the pharmaceutical companies are very interested in whether there's a danger of a crystal in a pharmaceutical product sitting on the shelf and gradually changing over time to another polymorph. So we've got this challenge of predicting the relative free energies, and this is where the experimental EU cost network, BEST CSP, is tackling the challenge to try and give us more accurate free energy differences between polymorphs for benchmarking the methods of the calculations. But before we can go into really accurate free energies, there is another difference that temperature makes. In real crystal structures, our atoms are moving all over the place. Well, not all over the place, but there are vibrations of different amplitudes which increase with temperature. And it may be that some parts of your molecule go into free rotations like methyl groups or large groups. And one of the reasons why the lattice, and we get so many more lattice energy minima than possible polymorphs, is that some of the structures, the barriers between them are so low that they will merge as you increase the temperature, or they will have merged by the sort of temperatures that you reach in crystallization. So we need a method that models how the crystals are actually moving to reduce our crystal energy landscape to the minima that will be distinct structures at ambient or practical temperatures, not at 0 Kelvin. And Matteo Salvaggio, my colleague, has been developing this with us. The input to his workflow is to take our CSP structures and any extra experimental ones there are and set up large enough simulation boxes for comparing the molecular dynamics of crystals of very different cell shapes and sizes. And the first test, because the molecular dynamics, to be able to do it efficiently, has to use a force field, is to check that the force field is adequately enough reproducing the CSP energy ordering and barriers that it's worth going ahead. But then you can do your molecular dynamics, first of all fixed cell, and then allowing everything to relax to see which structures melt and which structures coalesce to be the same. So we've got to develop fingerprint methods to be able to compare boxes of simulation boxes full of moving molecules, to be able to cluster them and get out a central CIF file, equivalent to crystal structure, static picture as the center. And then we can do some more molecular dynamics, metadynamics, and other things to look at the cluster center structures to see whether they're separated by sufficiently high barriers that we think they're likely to be practical polymorphs. So to give an example of this workflow, I'd like to talk about succinic acid, because it was one of those phone call moments. Nick Blagden phoned me up to say, Sally, my student is trying to use succinic acid to co-crystallize and therefore purify output from a peptide synthesizer. Only one of the crystals he pulled out is a new polymorph of succinic acid. Can you predict what it is? I accepted the challenge on the grounds that they would look to get more sample of this crystal structure to be able to determine the thermodynamics. And poor Paolo did try everything, but has never reproduced another sample of this polymorph. But we have one perfectly good crystal structure, and the interesting feature was that in this new polymorph, succinic acid was bent, where it's planar in the alpha and beta polymorphs that were known. It was relatively easy. The new gamma polymorph was readily predicted as being between the most stable beta and the known metastable alpha form in the crystal structure prediction. Looking at the conformations, Matteo's molecular dynamics confirmation agreed with the limited experimental evidence that actually this bent conformation is more dominant in solution, though transitions to being planar are very facile. So we didn't really have an explanation. We applied this temperature reduction. So this shows the minima, the lattice energy using the Gaff force field, and within that force field, a few of the structures melted. And then by doing the 300K clustering, there was a lot of amalgamation. The size of the sphere tells you how many of the structures coalesce to those structures. And so we reduced 101 to 27 plausible structures. Still an overprediction of more structures, but the gamma was still perfectly good as a structure, and we couldn't find any reason why gamma was not found again. So it looked as if it cannot reproduce the conditions with impurities that allow gamma to nucleate and grow to single crystal diffraction size without transforming to the more stable beta form. And we'd be very interested if anyone else finds this gamma polymorph in their experiments. But the key result is there are still more structures that appear thermodynamically competitive with the known polymorphs than are known. And so to summarize the challenge to get a crystal structure prediction code that actually predicts the crystal structures that can be found experimentally and over there is a huge challenge that's going on different axes, from going to more and more complex systems, both in terms of the size and complexity of the molecule, but also multi-component forms. This is a drug chloride structure with a dialcohol in it. Also, not only doing that lattice energy, but a lot of challenges in getting the thermodynamics right. It's easy in the computer to put on the pressure. Those are very difficult experiments to do. It's impossible for even the best theoreticians to assemble experimentalists to not include temperature in their experiments and to construct their crystal from the isolated molecules at 0 Kelvin. But it is rather difficult for the theoreticians to put in the temperature effects realistically for many molecules. But there are also other thermodynamic effects. Aurora Cruz-Cabeza has shown in some cases where the thermodynamic stability changes with the size of the crystallite, that you need to model the size because of the different energy of the surface structure relative to the bulk crystal structure, and relative humidity can make a difference to the thermodynamics. But as we're also over-predicting here, it's not just thermodynamics that counts. It's the relative kinetics of the nucleation and growth of the different competing polymorphs that need to be favorable to find a given polymorph. And so we need to be able to the aim of CSP would be to be able to take our thermodynamically stable structures and be able to predict how you could find them, or be able to convincingly eliminate a structure as it's unlikely to ever be able to be found. And this is a challenge because of the difficulties in finding all polymorphs experimentally. This is quite an old list of all the different methods that can be used to generate new polymorphs. It's not inclusive. We had a EU Horizon 2020 grant to look at the effect of magnetic fields on polymorphism after this list. But it's dominated by crystallization from single and mixed solvents, which can be done by high throughput robotic screening. But you can see in the list, there are a lot of other things like applying your lasers, supercritical fluids. And I'll be looking at some of the aspects where you have something else present. And incidentally, structure prediction what we do in the computer cannot influence what's crystallizing, but it can influence the people looking for the polymorphs. So we can use CSP to design certain experiments to find targeted polymorphs. One of the earliest CPOS puzzles was that carbamazepine had 4 known polymorphs, all of which had this hydrogen bonded dimer in the structure. And other CSPs said that there should be hydrogen bonding K-tamers that were competitive. And Alistair Florence's group looked at and found that dihydrocarbamazepine, which only differs a little chemically from carbamazepine, just changing that double bond, did indeed crystallize in one of these K-tamer structures. So we took form 2 of dihydrocarbamazepine as a template and then sublimed carbamazepine onto it. Now, some of the growth continued on the surface as laterally grown crystals, but there were vertically grown crystals sticking out, which indeed proved to be form 5, a catameric form of carbamazepine. So we can play this game again using the CSP. Cyheptamide, when we found that there was a structure, again isomorphous with dihydrocarbamazepine form 2, between the 2 known polymorphs, we tried the subliming again and got the structure we had predicted. Brilliant. It is very demanding of how close a match in energy and structure. We also looked at the phenamate family, which had been heavily studied for polymorphism. And when we started, sulfonamic acid, which has a chlorine, and mefenamic acid, which has a methyl group here, that's about as chemically similar as you can get, but they had no isostructural polymorphs until our CSP suggested it would be worth taking mefenamic acid form 1 crystals and subliming sulfonamic acid onto it, and that got us sulfonamic acid form 6 as an isomorphous structure. This is just cube, just gives you how many molecules in a 50-molecule coordination sphere can be overlaid within moderately loose tolerances. Working with such similar structures, we found some novel solid solutions, and one of them could be used to template yet another polymorph of sulfonamic acid. And Alistair Florence's group wanted to be sure it wasn't just the effect of sublimation, but when they sublimed onto copper, they got yet another polymorph sulfonamic acid form 8, and there has since then been a form 9 discovered by Aurora Cruz-Cook-Bezos group. Surfaces do have an effect. This is an observation by atomic force microscopy of what happens to olanzapine when you put it in water. So what Monica first observed was that there were little hillocks growing on the the edges on the surface of olanzapine form one. And with time, these hillocks evolved to orientated crystals of olanzapine dihydrate in the most stable polymorph D, nicely orientated and aligned. Whereas when there was any stirring, which is of course what you usually get when you're trying to dissolve olanzapine, the hillocks became droplets and solutions which crystallized to the dihydrate again, but the kinetic form B. So we had the challenge of rationalizing what's going on here. Why is the surface having this effect? Well, the first thing we did were quite simple calculations using the same model as the CSP, using the dimer and using Orient to model the ledge of the surface. And the most stable way of introducing the dimer was into its crystallographic position. But there were also a lot of other positions of the dimer on the ledge that were rather more stable than putting the dimer in its crystallographic position on the pure surface. And this sort of explains why you were seeing these droplets forming at the edges. And this aspect of having a two-step nucleation where your molecules get together and densify as one step, and then the nucleation takes place, you can see is likely to be very common when your molecules are far from spherical and are not, as you do in classical nucleation theory, going straight into the crystallographic site on the nucleus. We could also do some rationalization by doing nanocrystal modeling of the olanzapine flat surface and little nanocrystals of the two dihydrate structures on top of it. And this energy as a function of angle shows that the dihydrate D, the more stable polymorph that was found, had a kinetic preference for being on the surface and in the orientations on which it was observed relative to the kinetic form, where there are some crystals, but they've just fallen down from solution and aren't orientated. So we've got a bit of a rationalization of how the surface of the olanzapine is affecting the polymorph of the dihydrate that crystallizes. But I think this gives you some idea of the problems of considering everything involved in primary nucleation. Remembering that the big problem in polymorphism for the pharmaceutical companies is where you have a very late appearing polymorph that once you have the seed crystals of that polymorph and it has been crystallized the first time, causes you to lose control of your production process. And a lot of these late appearing polymorphs have been attributed to some sort of impurity templating the first nucleation. There is an interesting paper showing this rather surprising effect, led by my colleague Kresho Bukhar, who had been absolutely convinced that caffeine should form a co-crystal with the benzoic acid. But he couldn't make it happen. He got Graham Day, who did the CSP, and yes, you know, it should be forming a co-crystal. That was going to be much more stable than crystallizing as the two components. Then Kresho had the idea and introduced some seeds of fluorinated benzoic acid. And soon in his lab, he was able to produce the co-crystal, the one that had been predicted, regularly without introducing the seeds. He then got 3 other labs who were good at co-crystallization around the world to do exactly the same experiments, and they too couldn't co-crystallize for the first time without introducing some heteronuclear seeds. But after a few times, you didn't need to explicitly seed. Whilst talking about some of Graham's work, I would like to refer to the CSP aspect of designing new materials with desired properties, because Graham had been working with Andy Cooper's group up in Liverpool for long enough, with enough trust, that they actually synthesized a molecule for the first time after the prediction from the CSP landscape that it should form this highly porous solid. So every point on here is a crystal structure of this molecule from the CSP, but here the pore dimensionality has been colored onto the crystal. So you can use this to display properties. And the one they were after here was metastable in the CSP. It did indeed have the lowest density reported for a molecular crystal at that stage. And its formation was because it was stabilized by all the solvents in the pores. So it did crystallize out. And indeed, finding the most stable crystal structure, which is also the densest, proved to be very hard to crystallize and only came out after they'd published the Nature paper on this. So I hope I've given you a sense of the fun of crystal structure prediction and working with experimental some of this. Over the past 20 years, we've done a lot of CSPs. Our group is biased to small rigid molecules and those with known crystal structures. And we've been doing a lot of updating of this, sometimes when the CSP methods improve, sometimes when then new polymorphs are found inspired by CSP. And indeed, at the moment, we're translating our database into a new format. And so if you do have any new crystal structures and polymorphs of structures we've studied, we'd love to hear from you. But one of the things we've found is how molecule-dependent crystallization is, and how crystal structure prediction is very much evolving alongside improvements in solid form screening, detection, and a lot of improvements in characterization capabilities. So to conclude, what is needed for confident prediction of polymorphs? Well, CSP calculations as they now stand will provide you with guidance about the range of possible polymorphic structures, but it's telling you nothing at all about the kinetic competition in nucleation, growth, and ease of transformation to the most stable. If the most stable CSP-generated structure cannot be found experimentally, then at least its computed properties may help design a route and aid detection. And it can be, Doris Brown has one example of this, where you can find the more stable predicted form and then be able to show experimentally that actually it's not kinetically going to compete and be a problem for the more readily stable, though strictly metastable structure. But you can see the challenge of making this a purely computational prediction, of being able to predict nucleation growth rates for all accessible crystallization conditions for a molecule. There's a lot for the theoreticians to do. We need more accurate potential energy surfaces. or force fields. We want to be able to model the moving crystal structure. I've illustrated how this is necessary to reduce the CSP structures to those that are free energy minima at ambient conditions. And we also need it for improving our predictions of the thermodynamics of the different structures and solubility predictions, as well as we will need it for modeling nucleation growth rates. And this, as well as the most accurate methods of evaluating the lattice energy, is a challenge because we will need to be reflecting the energetic effects of how the molecular charge density distribution changes between the different phases and polymorphs of a molecule. So there's got to be more close collaboration between experiment and theory, but it is helping, giving us a sense of understanding of the challenges of crystallization for Pacific molecules. So that's my conclusion, and I've got a lot of grateful thanks to all the people who have been co-authoring the papers that we've been developing over the last couple of decades. Thanks to quite a lot of people present who have helped by discussions in workshops, conferences as well, when they didn't lead as far as publications. Some major, Louise Price has been with me for over 20 years as our technician and the master of our database. Rui Goa now with Pfizer, Nicholas Francher now with CCDC, and my colleague at UCL Chemical Engineering, Matteo Salvaggio, have played a lot of contributions to some of the more recent work I've shown. And we've had a lot of lovely collaborations with Alistair Florence and his group in Strathclyde, and also Susan Reutzel-Edens and her group when she was at Eli Lilly. This doesn't happen without a heck of a lot of work on the computer algorithm development, which has been going on continuously. I particularly want to thank Claire Adjman and Kostas Pantelides at Imperial, whose algorithms, Crystal Predictor and Crystal Optimizer, we have been using and beta testing with them. These used DMA-Cris, the crystal structure modeling code that's been developing with Maurice Leslie, and Graham Day has contributed a lot to when he was a PhD student and since then. And I'd also like to thank my supervisor, Anthony Stone, whose distributed multipole codes are central for the evaluation of the molecular forces, and his code Orient that models other phases other than the crystalline state has been featured here. We've been lucky that the CCDC has organised the blind tests, because that's made a huge difference, and we do learn from the different participants, and there are so many now different approaches to doing crystal structure prediction, and funding, some from Eli Lilly and quite a lot from the UK's research councils over this period, starting with the big CPOS grant in 2004. And thanks for your participation and interest in this, and I'll try and answer any questions.
Thank you very much, Sally, for this beautiful lecture and really fascinating topic. And probably some questions will appear soon, but before they will appear, let me comment something. In my opinion, the whole field also requires bigger challenges than just structures from CSD, because this structural information, which is in CSD, for years has been collected up to only limited resolution, and this and only taking into account Bragg diffraction. So this means that all the structures are, say, beautifully periodic, etc. But if you how about predicting structures with diffuse scattering at high angles? And when your molecules will not be so nicely periodically located, but will be staying over the symmetry elements, try to predict this kind of structures.
So, first of all, one of the major things that needs to be conveyed for theoreticians is not all crystal structures are the same. Yep. Most of the majority of crystal structures, you have limited knowledge about where the hydrogens are. They've got to be corrected. There's going to be a systematic error of it. Increasingly, with quantum crystallography, you are going to get far better crystal structures out of it without that need. But you're referring to the diffuse structure scattering and the problems of disorder. And that is a major challenge. We do see it as an aspect of CSP you may be getting in multiple minima that give you a hint of the disorder. So, for example, looking at the CSP in cyclopentane, we could attribute that there were a lot of crystal structures that were essentially, by the time you were at high temperature, rotating so much that you have the dynamically disordered phase. But there are a lot of different aspects of both static and dynamic disorder that you sometimes get clues from CSP that this may be possible. There's something to look out for because you can see the relations of the crystal structures. But dealing with dynamic versus static disorder from its thermodynamics is difficult. And disorder is the really big challenge. And that, I think, was one of the things that came out in the last blind test, was how many of the structures had disorder in at least one of the polymorphs.
Mm-hmm. We have some questions from Hans-Bert Birgi, thank you, and from Kamil Dziubek. Hans-Bert Birgi, from a practical, not an academic point of view, what is more promising, faster, cheaper at present, experimental or computational polymorph screening for a new molecule?
So part of what was behind that digital design was the hope that the pharmaceutical companies would be able to see which molecules might be very difficult to develop an acceptable crystallization strategy from, and with the possibility that there might be one that from the biological side was virtually the same but could be developed quickly. And a lot of the investment in computation is to help things faster, but doing the sort of CSPs for drug-like molecules that are commissioned by the pharmaceutical companies is very expensive in the amount of CPU time. If you use cloud computing, that can considerably cut down the length of clock time, real time, that it may take, but it's still quite a long period. But on the other hand, some molecules prove very, very slow to get any crystal structure from. Sometimes that may be a matter of impurity. Others, the polymorph screening can go. They'll do a certain amount and would love the CSP to tell them your polymorph screening is complete. Yep, there's no risk. You can finish. However, doing the calculations, they may find you've got to keep on extending your polymorph screening because there is predicted to be another polymorph that could threaten the development of the form you want to develop. So it's very much an ongoing structure. A lot depends on your costing model. The extent, the costs for commercial screening using robotics, blood crystallization experiments versus what people might do by hand, and the number of cases where the polymorphs come from the experimentalist observing that there are signs of polymorphs. Roy stands out because you can see there are new polymorphs. The problems are when your polymorphs are colorless, which most crystals are, and have similar morphologies. Then it's a matter of they're harder to spot what you've got there.
Thank you. Now we have a question from Kamil Dziubek. Kamil, you try to simply to ask this question yourself.
Hello, can you hear me?
Yeah.
Perfect. Thank you, Krzysztof. I'm wondering. Actually, you showed a lot of really nice examples, and I know, of course, examples throughout your scientific career and experience with crystal structure prediction, of comparison of the prediction to the crystallographic structures. I mean, to determine structures which are in the crystal structure database, or which can be for the crystals that can be actually determined with X-ray diffraction. But not all of the samples can be determined with single crystal diffraction. And there is a lot of examples of powders or partially amorphous samples, and let's put away the amorphous samples, but the powders that are not only polymorphs, but sometimes a mixture of phases. One of the examples that you showed on this, when the crystals were actually forming from another phase, that was if you actually make an analysis of test of as a powder, it would be a mixture of phases. I'm just wondering how you can actually how precisely you can predict such cases, and can you actually can facilitate phase analysis for the powder crystal diffraction with your method of crystal structure prediction?
So let's talk about crystal structure predictions as generated by the community. Yeah. So you can easily generate a powder pattern from the crystal structure, the CIF files we get out of the CSP. They are not going to be that accurate, and the problem with powder is it's very sensitive to temperature and getting the cell dimensions exactly right. But Jonas Nyman and also Erin Johnson, there are a couple of methods of allowing for that, to try and see which powder patterns will best match the structures, and being able to pick them out and then get the CSP to give you a starting model to start doing the refinements. You have to be even more expert at the powders, but you can use these structures, a knowledge of one and the other, to do impure phases by subtracting one known phase from the other. And so using the CSP structures for an aid to solving structures from powder is a developing field, and is a powerful technique in the hands of those that understand the two methods well. And there are increasing codes dealing with that. So yes, powder patterns and working for powders, and also there's a whole group of NMR crystallography, of the extent to which you can, from the NMR signals, be able to determine the structure. And there's some very nice studies where people have combined the two. So your NMR, solid state NMR, will help you with the level of phase purity, whether there's amorphous there, etc. So combining the two in there.
Thank you.
As far can I comment as far as NMR studies are concerned? When I was doing also combined studies of NMR and X-ray diffraction, and I would say that you need X-ray diffraction to confirm NMR results, but I wouldn't agree that the other way is correct, because I can easily pinpoint examples when you can't differentiate with NMR situation whether you have in your crystal two independent halves of molecules in special positions, or you do have one dependent molecule in your crystal lattice. And with NMR, it is impossible to differentiate this, whereas from X-rays, you will immediately see which is the case. So that's one comment. And
so it was one of the cases Glastab, you can get multiple powder patterns, multiple structures that fit the powder pattern. Then the NMR can help you distinguish. I think it's putting the three things together is what you could end up getting confidence in your model. If you get the calculations, the diffraction, and the solid state NMR together, you're putting together the pieces of the puzzle. And if they all fit, then you have more confidence.
Fully agree. That we have next question from Daniel Kamiński. What do you think about polymorphs prediction using neural networks?
Neural networks, AI, machine learning, that whole set of things is having an impact. Mark Tuckerman, they did a little bit of work for the 7th blind test and have since published a method that's looking very promising based on the data in the CSD and doesn't do the lattice energy evaluations. So that sort of method is bubbling up. There's a lot of work on using neural networks, other machine learning, to learn from one potential surface to correct it to a more accurate one, and to cut down some of the times and speed up the calculations, which are so expensive. I mean, you might be able to learn from one surface, do another, do that for doing a lot of minimizations of your structures, and then refine the ones you're really interested in as a hierarchical method. So there's a lot can be done in both ways. a paper we've recently submitted has been using the CSP and polymorphism studies on 20 molecules. We've reduced a test data set that some of our colleagues have used to evaluate some MACE machine learned potentials against that data. So that's going to more force field like fast runs, but also it helps. There's still a long way for bottling out and getting really accurate lattice energies as well as accurate free energies and looking for phase transitions. So they've got their methods, and experts using these systems are making progress. But anything with computers, you need to know exactly what you're putting in and assuming to evaluate what you're getting out.
Okay, thank you. Paulina, do you want to ask a question? Yes.
Yes, I want to come back to this problem with powder samples. We have now a new player, electron diffraction technique, which is able to deliver you a crystal structure from nanocrystals. Do you see that this method is getting importance in crystal structure prediction at polymorphics?
Oh, yes. There's a lovely paper, Bill Jones and his group found a polymorph of theophylline from looking at electron diffraction, saw a different morphology, calculated the electron diffraction, combined that with the CSP to solve the structure. And there you had crystallites of a new polymorph below the limits that you could have detected from powder. And so I think people looking with electron diffraction are likely to be finding and characterizing a lot more polymorphs. It has been used to finally get a crystal structure for one of the olanzapine polymorphs. So it is going to give us more structures that are known, and it will be very useful for systems where you don't have phase purity. You've got different crystals and can observe it. Mm-hmm. So I think that is going to make quite an change to our understanding of the frequency of polymorphism, or what we mean by how readily you can get a phase pure sample. Mm-hmm. But still, we won't be finding all the CSP generated structures.
But definitely this will fill in a big part of this energy landscape of those points, missing points, which at present haven't been found. But because we can see that we are getting also different symmetries than the most common ones for those tiny crystals. So it's quite a common phenomenon. Anyway, I wanted to ask you at certain moment referred to this multiple molecules in independent part of the unit cell or in crystal lattice. How about predicting such systems? Is this possible, or it's at present a challenge? And if you would have, say, 4, 8, sometimes there are even more than 10 moieties in independent part of the unit cell.
Yeah, that is the challenge, that it is so much more computationally demanding. So this can be either two independent molecules in the asymmetric unit, often potentially with two very different conformations, where the flexibility is then coming in, but it can also be multi-components done for fixed stoichiometries. But there are some assumptions you're putting into your CSP, but clearly your z prime equal 2 search will have to generate all your z prime equal 1 structures and then more some. So the computational cost of the generation and evaluating the structures in the hierarchical manner goes up, and your data handling gets harder and harder.
Sally, I have an ultimate test for crystal structure prediction. These are polymorphs of ice. There are 20 polymorphs of ice. Can you predict? Can you predict them? That would be quite something.
No, but I know some people who may arguably can. So ice is one of the most studied systems, and indeed a couple of my colleagues at UCL have been involved in ice predictions and discovery of new phases, some of the new phases of ice.
Salzman, for example.
Yes, Christoph.
Yeah.
Yeah. So yes, they do. You can have fun debating with the ice experts, and there are a lot of people who have devoted their life to the intermolecular forces in ice and its potential surfaces and ice polymorphs. Is ice actually that unusual, or is it just that there's been so much more focus on it? Yep. We have
5 million of papers on ice. 5 million.
Yep. Very important system, but there are quite a lot of other hydrogen bonded systems, alcohol hydrates, that have all the potential to be similarly complex.
Yeah, but even if you drink alcohol, you are adding ice. So anyway, that's fascinating system. At least for me, it's my hobby at present. So I love it. I do not see more questions. Paulina, do you have any other questions? If not, let me thank both our speakers today for beautiful lectures, for interesting discussion.